Okay, let's start. So, yeah, you can keep posting your question in this slido.com, and access code is KUDL. Okay. Yeah. So let me start with the question about the advantage of this max pooling over average pooling. So this is the operation of max pooling, right? And then suppose we obtained this kind of an activation map, and suppose this activation map was actually the result of applying the convolution filter of capturing this this directional edge, okay? And then in the case of our image size is currently 4 by 4, right? And then each of these numbers are indicating how strongly this particular pattern is occurring at a particular position, right? And then after doing the max pooling, so we are selecting the maximum value, right? And then using this value as the representative value of this entire region, or this 2 by 2 region, right? So in this case, it's the process of losing some information, because we had originally 4 different numbers, and then we had to represent a single number out of these 4 different numbers. So definitely we can do the average value to represent this 2 by 2 regions, but also we can choose this maximum value, right? And then these 2 different strategies has pros and cons, but the reason why we use the max pooling is because, regardless of specific positions, we want to transfer, or we want to pass the information of the strongest signal or strongest kind of occurring pattern of this this edge, right? So regardless of these 4 different positions, we do not care about the specific position, but the important part is how strongly this particular pattern occurred within these this small 2 by 2 region, right? So it is somewhat related to kind of a robustness of convolutional neural nets against a strong, slight positional variance. So I believe you guys have watched this kind of introductory video that uses this toy example. So if we want to detect this large X mark, and then there are some slight variations possibly in practice. So for example, it can be slightly having a different angles, and their size can be different, right? And maybe this X mark can be placed slightly on the upper right part. Okay, so those positional kind of slight variance in terms of their exact positions or angles or scales, we want to be able to be robust against those different variations, and be able to say all these patterns are having this X mark commonly, right? So in that case, suppose our pattern was like capturing this kind of pattern, and then when doing the convolutional neural nets, and then we will do the convolution operations like this, and then exactly like in this position we should have this pattern, but in this case it was slightly moved to the 1 pixel lower, right? But in that case, both of them we still want to say that there were really strong pattern of this this kind of edge pattern in this region, roughly in this region. Okay, so that's why we want to use the max pooling. Okay, but if we use the average pooling, if we do the average on this value, and then it will be around 3.5. So it's just a rough value. And in this case, even though this 3.5 is the can be better representative of 4 different pixels activation values, but this 3.5 can be computed from this pattern, or it can be computed from maybe 2.5 and 4.5 and maybe 3.5, 3.5. So in this case, the average value will be 3.5, which is the same value, right? So in this case, the strongest pattern was only like 4.5, right? Which means that in this region, this pattern was not strong enough in anywhere within this 2x2 region, right? So that way, we want to detect or capture the strongest pattern and their strengths as our activation to pass to the later layers. Okay, so that's the main intent or the advantage of using max pooling against the average pooling. Does it make sense? Okay. And then now next I want to describe a little bit about the new perspective of viewing the convolutional operation. Okay, so in this chapter 5 we studied the convolutional neural nets, and it seemed it looks like quite a different operation from the typical fully connected layer that we studied. Or how would we draw our computational graph and perform the backpropagation on this convolutional neural nets or convolutional layers. So let's look into that issue. So suppose we have 4x4 images, and then our filter size is just a 2x2. By the way, this is just a simple example, and that's why I use a 2x2 filter. But in almost all cases, we don't use this 2x2 filter, or in general, we only use the filter size as the odd number. Okay, like 1x1 or 3x3 or 5x5 and so on. And can anyone tell me the reason why we use the odd number for our filter size? 아는 사람 없어요? 네? 패딩이요? 네. 패딩이 좀 애매해져서? 네. 네. 또 다른 이유는 또 없을까요?
이미지가 보통 작수 사이즈여서.
이미지가 작수 사이즈여서? 네. 아마 네. 두 친구들 다 어느 정도 이제 맞는 이야기인 것 같고요. 자, okay, so the convolutional, applying the convolution filter is to compute the single value out of some patch or the size of that filter, right? So in this case, if we apply the 2x2 filters, and then out of these 2x2 regions, we will generate a single scalar value, right? And then even though we apply the filter onto these multiple pixels, or the regions involving multiple pixels, but we want to actually correspond like one-to-one relationship between input and output pixels. Okay, so in that case, we usually match or correspond. Yeah, if it was 3 by 3 pixels or 3 by 3 filter sizes, and then we will apply the convolution filter, and then the resulting scalar value can be actually corresponding to this center pixel. Okay, so now we change it each center pixel into a different values. Okay, and then if we guarantee or if we use the proper size of the number of the paddings, and then we can maintain this perfect one-to-one matching between each input pixel and each output pixel, right? Okay, so in that case, if we use the odd number of filter size, and then it would make sense. But in the case of an even number, and then this pixel should be mapped, somewhere around here, right? Which is like, not really corresponding to a particular input pixel. So that's why we typically use even number of filter size. Okay, so in almost all the cases of using convolutional neural nets, you can just assume that all the filter sizes are odd number. Okay, and then but just to simplify our example, let me just use the 2 by 2 convolutional neural nets at this moment. And then in this case, let me draw some fully connected perspective of using this convolutional neural nets. Okay, so in the case of fully connected neural net layer perspective, how many input nodes do we have? So even if we have an input as two-dimensional array, but we can rearrange them into one single one-dimensional vector, right? And then how we do it is we just cut them vertically or horizontally, and then put it or concatenate it into a single vector, right? And then we can have in total 16 different nodes in the input layer, right? And then in the case of an output layer, if we do not use the any padding at all, and in this case, how many output nodes do we have? Or the resulting activation map size will be 3 by 3, right? So if we do not allow any paddings, right? And then if we use this 2 by 2 filters, and then we can move like 3 different horizontal positions and 3 different vertical positions, and thus our activation map size as an output will have 9 different pixels, and so we have 9 different nodes as an output in an output layer, right? And then let's think of their connections. So in the case of this 2 by 2, applying this 2 by 2 filters at the upper right positions, and then suppose let me just enumerate the pixels as maybe 1, 2, 3, 4, 5, 6, 7, 8, 9, and then suppose this first pixel in the output activation map, and consider this, and then let's just consider their connections, and then it will be 1, 2, 3, 4, 5, 6, 7, 8, and so it's a 1, 2, and so these two are connected together, and then 3, 4, 5, 6, and those are connected together, right? And so this output, the first output node, or the output node 1, is only connected to these are 4 different input nodes, right? And then what about this second node, this guy? In this case, it is the result of applying the convolution filter at this position, and thus let me use different colors. So 3, 4. Nope. This and this, right? Okay, so that way we can view our convolutional layer as a special case of a fully connected layer where the input and output nodes are not actually fully connected, so they have a limited number of edges as a connection between input and output nodes, right? Okay, and then in that case, we can, in the case of fully connected layer, if we just assume that this link is originally there, but we can just treat the weight value assigned to that connection as just a 0, right? And then, we don't actually update that parameter because that is just fixed as 0, right? So that way we can view this as a special case of this fully connected neural net. And also another thing, another interesting thing is that there is the notion of the parameter sharing. Okay, so suppose this weight value was maybe 3, so it's 3, 4, 5, 6, and it is having the weight of 3, 4, and 5 and 6, right? And then also this blue lines that connects this output node 2 with the input node 2, 3, and 6, 7 will also have the linear combination weight as 3, 4, 5, 6, right? So that way, even though we see multiple separate connections, but their edges are actually shared, right? So more exactly, this fully connected layer can be drawn in this form. So in the case of this linear combination, and then we can draw this computational graph as this form. Right? Okay, but what about this parameter is actually A, which is the same as the linear combination weight assigned to the different variable x1, okay? And in that case, A1 is connected with the x1, but it is also connected with the x2, right? This one is gone, right? Okay, so this is the computational graph when we use the shared parameters, right? So if we extend this into this form, and then this 3 will have our parameter A, and then it would have been multiplied together with the first node, and then also this guy. So this second node will have its own parameter, maybe B, and it is multiplied together. I mean, that is the original form of a fully connected layer where we have our own parameters assigned separately to each variable. But in this case where we have a shared parameter, this common A is connected with the first node and also second node. I mean, when generating the second convolution activation output, right? So that way, even though we have many different connections in this fully connected layer, how many parameters do we have? So we only have 4 different parameters. So they are connected properly in a shared form with the multiple different inputs, right? So does it make sense? Okay, and then how about the backpropagation? So in the case of a backpropagation, the gradient would arrive at each different output node, right? So this node and so on, right? And then those gradients arrived at the different output node will be actually merged into just a single parameters, right? Because so it's a little bit messy, but let me see. So this is our output node, and also this is our second node in our output layer, and then we have dy1 and dy2, and then we will do the backpropagation, and then because this A has the multiple branches, and then the gradient will be merged together into the single parameter A, right? So this is how we update or perform the backpropagation and parameter updating on our convolutional filter weights. Okay, so more exactly, those 3, 4, 5, 6 are our filter weights, or the shared linear combination weights in this special fully connected layer form of, that represents the convolutional layer. Any questions? 네. 네. 파라미터요. 여기서는 이제 필터 사이즈가 이제 2x2니까 이제 거기 하나하나의 정의가 되는 파라미터가 이제 4개가 있는 거죠. Okay, so the number of parameters are actually the same as each individual ways in our convolution filter. So in this case, it is a quite simplified form where we have a 2x2 convolution filter, but what about the depths? What if we involve the depths? Suppose we have this input activation, and then suppose our filter size is 3x3 by 5, which is the same depth as the input activation map. And then, these are the number of parameters that we have to do the gradient descent update, right? And so we have 45 different parameters. Okay. And then here, I missed one thing. One more parameter. What is that? Right. Bias term, right? So back to this fully connected layer. So in this case, it is just a linear layer, but not affine layer, where we allow the bias term. So in that case, we have an additional input node that has just an input value as 1, and then we have this kind of bias term that is represented as a weight value assigned to the input node of this scalar value of 1, right? And then usually in the case of a fully connected layer, those weight value assigned to this input node 1, which is our bias, will have the number of output nodes. So these bias value will be all different value, right? Because they are all separate parameters, right? So this is an x1, x2, and y1, and y2, and here 1, and then y1 could be 2x1 plus 3x2 negative minus 5, and then y2 will be like this, and then the bias for this is having the weight as negative 5 and this as 2, right? But what about this convolutional neural nets or convolutional layers? All these weights are also shared as a single parameters. Okay? So that means suppose we have this kind of activation map, and then our filter is maybe 1, 1, 0, 0, and then suppose our bias is maybe 2. Okay, and then we typically do the inner product on this position, which will be computed as 5, right? So this is the inner product value, right? And then we will add this bias term. So 7 will be our activation value corresponding to this position. And then how about moving the convolution filter to the 1 pixel right? And in that case, we will do the inner product on these 4-dimensional vectors or 4 different numbers. And so 2 and 7 will be added. And then the same bias value will be added finally, okay? So that way, bias term, which is our scalar value, is assigned to as a single shared parameter to a single convolutional filter, okay? But what about having a multiple filters? I mean, typically in the one convolutional layer, we have multiple filters, right? And so suppose we have a first filter that has the activation map as a 2-dimensional array, and then suppose another we have another convolutional filter that also has the same size, right? So this is another set of parameters, and also we have one more bias term assigned to that second convolution filter, right? But you can easily extend or draw or imagine that situation as which is a general kind of convolutional layer from this fully connected layer perspective. Okay, does it make sense? 이해돼요? 네, 돼요? 예. 질문 있는 사람? 마지막으로 가지는 값이 웨이트를 가지느냐, 웨이트 역할을 하느냐. 네, 일단은 okay, so this is the typical way of stacking convolutional layers with the ReLU and the max pooling and so on. So we first apply the convolutional layer, and then that is just a linear transformation or just a fully connected layer, right? And then as I mentioned in the previous lecture, we do not just concatenate two linear layers. We always add nonlinear units in the middle, right? So that nonlinear unit is usually used by this ReLU, adding this ReLU layer in the middle. And then we also do the convolution. So in this case, comb ReLU and comb ReLU, and then this max pooling is just occasionally added. Okay, so it's not always added at the end of convolution and the ReLU layer. Okay, so max pooling is actually the operation of losing some information. So as I mentioned in the previous example of this, so from this operation, yeah, we are losing some information because we just reduced 4 different numbers into one numbers, right? So that is like losing a lot of information. So we just use this max pooling layers sparingly. I mean, not all the time. Okay, not every time after this conv and ReLU, but ReLU is always follows the convolution layer. Okay, so ReLU always follows the convolution layer, but max pooling is yeah, just occasionally added. Okay. Okay, and then yeah, conv ReLU and max pooling, and also we can add this conv ReLU and max pooling, and then suppose we obtained like 2 by 2 and 3 as our activation map. Okay, and in that case we now change it into the fully connected layer phase. Okay, so at some point we no longer use a convolutional layer, but we just apply the fully connected layer. Okay, and how we actually just yeah, represent all these 2 by 2 by 3 tensor kind of shaped array into one single vector, right? And how? Yeah, we can just put these numbers. Yeah, this guy into here, and also we have another vertical 2-dimensional vector, and that will be added at the end, right? So that way we can vertically stack all these numbers into one single vertical vector, right? And then we apply the fully connected layer after then, okay? And then if we do the binary classification, and then it will just be multiplied. Yeah, so okay, so yeah, there are some fully connected layers following this conv ReLU and max pooling, and then to find if we do the binary classification, we can obtain or stack the linear layer that has the single output node that has the nonlinear unit as the sigmoid. Okay. Or if we have a multi-class classification, and then we will have a output layer that has the same number of an output node as the number of multi-class that we have. Any questions?
교수님 아까 그 shared 파라미터 거의 설명하신 게
네.
그래서 결국 뭘 하려고 하는 건지 모르겠어요.
shared parameter로
왜 하시는지.
네. So the meaning of viewing this convolutional layer into, I mean, from the fully connected layer perspective is because, I mean, so yeah, let's just use, I mean, let's just ignore or let's just not use a convolutional neural nets and just try to build up some fully connected layers or fully connected neural nets in order to perform this image recognition. Okay, in that case we would just stack the fully connected layers, right, instead of using a convolutional layer at all. And then what is the advantages or disadvantages of using just a fully connected layers instead of using convolutional layer at all? So first of all, the parameters are, I mean, the number of parameters will explode, right? Because there are so many number of input pixels as well as the output pixels, right? So that way, yeah, we would require a lot of parameters just for the single layer, right? And also, if we use this fully connected layer, and then yeah, we don't have any flexibility, just like, we don't have any flexibility that this max pooling has, right? So those max pooling will make sense when maintaining our activation map as this two-dimensional map, or if we consider the depths, and then a three-dimensional activation map, right? And then we intentionally apply the max pooling and lose some information intentionally, so that we can add some robustness to our model, right? But in the case of fully connected layer, every different node will have their own fixed parameter value that is assigned, right? And so if this kind of edge pattern appeared in a slightly different positions, in that case, their own parameters, I mean weight parameters assigned to that different node will have their own parameter values, and thus our model will not be kind of flexible, right? Yeah, so this convolutional neural nets will mainly add some flexible kind of pattern extractor, okay, regardless of slight variations in terms of positions, and maybe some angles, or some sizes and so on. And also there are if you study maybe chapter 9, maybe sometimes next week, then you will see some advantages of using multi-layers. I mean, so let me just discuss this situation. Suppose you have a fixed total number of fixed parameters. So you are allowed to use maybe 10,000 different parameters, okay? And then, so input nodes are maybe 10 different nodes, okay? And then suppose output node is just a single one, okay? And then there will be many choices. And then let's just use one hidden layer, okay? And then we can add a lot of parameters and a lot of parameters over here to use up 1,000 different parameters, okay? And then this is one design choice, but also the second design choice will have maybe two different layers, and then we have parameters over here and so on. But in this case, if we use the two hidden layers instead of one, and then those two, I mean the number of nodes in these two hidden layers will be less than the number of nodes in the single hidden layer, right? Because we have a fixed limited number of parameters that we can use, right? And so if we're going to use a single hidden layer, and then we can use a lot of parameter, a lot of input node, the nodes assigned in the hidden layer. But if we use the two hidden layer, and then we have to have a parameter over here and over here and over here, and so the number of nodes in the two different hidden layers will have a relatively small number compared to the single hidden layer case, right? So in that case, which one would you prefer? Okay, so using one hidden layer and having a lot of hidden nodes within that single layer, or using two hidden layers but relatively small hidden nodes in each layers compared to the first case. Which one would you prefer? So usually the second case is preferred, of having more layers compared to the more number of nodes within a single layer. And the main reason is because by adding more layers, we can actually add more nonlinearity, okay? Because if we add one more hidden layers, and then it means after that hidden layer, nonlinear unit is always following that hidden layer, and thus those linearity limitation can be kind of extended, or we can represent more flexible or complicated patterns that we want to learn, okay? But in the case of a single hidden layer, yeah, so we have only one spot where we can add non-linearity because we have only one hidden layer. Okay. Okay, so that is the spirit of this VGGNet. So this same kind of same consideration can also be applied to the convolutional neural nets, right? So suppose we have a fixed number of parameters that we are allowed to use, and let's think of just one single convolutional one convolutional layer, and then because we have many number of parameters, and then we can use many parameters, and thus we can actually use much larger filter size. Okay, so if our filter size is maybe 7 by 7 and maybe 3, and then our parameter values will be 3 squared and times 3 plus 1, which is our bias value, right? And then maybe the filter size, right? So this is the number of parameters that we need in order to design one single convolutional layer by using this 7 by 7 filter size. But what if we use the size as maybe 3 by 3, which is much smaller than 7 by 7? And in that case, within a single layer, by using the same number of parameters, same number of filters, and then the number of required parameters will be much smaller. And then if we have this fixed number of parameters that we are allowed to use, and then we can maybe add second convolution layer, right? So in that case, the second case is much preferred because we can introduce more non-linearity, right? Because we added 2 layers, and thus non-linearity can play their own role at 2 different positions, right? Any other questions? 뭐 질문 있으면 좀 자유롭게 하세요. 이게 또 수준을 어디에 좀 내가 맞추고 이야기를 해야 될지 좀 감을 좀 잡는데 도움이 될 것 같으니까. 네. 질문 있어요? 뭐 쉬운 거라도 좋아요. 네. Okay, and then in terms of using the convolutional layers, we basically have the filter size, right? Filter size of maybe called f, and we usually use the squared shape of a filters. So f by f, and then also the depth is automatically determined as the input activation maps depths, right? And f is our parameter, and another parameter is stride, right? So those stride is so in this case, if the filter was applied over here, and then if we have a stride size as 1, and then the next convolution will be applied over here, but if our stride size was 2, and then it will be applied like this. So from here, so our step size in terms of the number of pixels that we move at each step is 1 or 2. Those are the meaning of the step size, right? The stride size, okay? So we have this stride, and also we have the number of paddings that we can use, right? And so suppose our image size is 100 by 100, okay? And then we can think of kind of resizing operations of the given image. Okay, resizing operation. So so if our original picture or photo has really large resolution, and then we would sometimes resize it, right, so that it can have a smaller resolution, right? And so given this 100 by 100, and then suppose our output image is resized by half per horizontal or vertical axis, okay? And then this kind of resizing effect can be controlled by mainly by this stride size, right? Okay, so the stride, so we have a single pixel over here that will generate the one single activation map output, and then if we move one pixel to the right, and then we will have the output corresponding to this pixel, right? So roughly in that case, we do not resize, or we do not make the image size small, right? So in this case, roughly the image size will be staying the same, okay? But if we do the stride size as 2, and then after getting the output for this pixel, and then we move 2 pixels away, and then obtain the output for that pixel, right? So that way, the multiplier of 2 is applied over here, right? So that way, the activation output, is the number of an activation output is roughly having the half the size of the original one, okay? So this stride size is the main kind of a tuning controlling knob that you can resize your image by half, or maybe if you want to reduce the image size as 1/4, and then the stride size will be 4, okay? And if our filter size is relatively larger, and then so in the case of 3 by 3 pixels without any paddings, we cannot have any activation output corresponding to this border pixels, right? But those border pixels can be considered as a kind of minimal or very small if our image size is really big, okay? And then removing slight those thin borders will not change the image size much, right? So this image resizing is mainly done by stride, but also this filter size may have a slight effect of decreasing the image size, but we usually supply the enough number of paddings, okay, so that the image sizes are staying the same, okay? So you guys know that in the case of 3 by 3 filters, and then we need one as a padding size, right? And if it was 2 by 2, and then we would provide 2 paddings, okay? Okay, and also, if we use the convolution layer with the stride size of 1, and then my conclusion, or in summary, if we use the stride size as 1, and then convolution layer doesn't reduce the image size, right? And then in our entire convolutional neural nets, this image size is reduced by a particular layer, which we already saw as the max pooling, right? So this image size is resized or decreased by half by the max pooling layer, okay? So conv-ReLU, those layers do not reduce the image size, but also it can increase or decrease the depth of our activation map, but still image size will roughly stay the same. But when applying the max pooling, and typically we use a 2 by 2 max pooling, and then that's when the image sizes are getting smaller by half, right? So I think I showed this VGGNet figure earlier in the lecture, right? So In this case, our original image is a 224 by 224 and having the depth of 3, which correspond to RGB, right? And then this first one of the activation map is the result of one single layer of convolution and ReLU. Okay, and then this image size, the width and height stays the same, right, as 224 by 224. And then we apply another convolution layer and the ReLU, and then it still make the image size stay the same. And then at this red activation map, now image size got smaller, right? So that's when we apply the max pooling. Okay, and so if we read the number, and then the number is 112 and 112, which is exactly half of this 224, right? So you can roughly now see or read the convolution neural net structure from that activation map kind of pattern of changes, like conv-ReLU, and max pooling, and also conv-ReLU, and max pooling, and so on, right? And also, so if the output activation map is having the depth of 64, and then it means the convolution layer in the middle has how many convolutional layers, how many convolution filters? 64, right? So at this conv-ReLU, we have a 64 convolution filter, and at this position, we also have 64 different filters, because still the output has the activation map of the 64 as the depth, right? And then after doing the max pooling, and then now the channel size has increased into 128, and that means after this point, we now use the convolution layer that has the number of filters as 128. Okay, so it's like we intentionally lose the spatial resolution by half and so on, right? So that's the main intent is to be able to be flexible on the slight variations of their positions and so on, of the patterns that we want to capture. But at the same time, at each position in our image, which is a resized or a smaller sized image, at each position, I mean, one pixel is representing much larger regions in the later layers, right? And so for that pixel, we kind of represent the, we want to capture many more different patterns by using more number of convolutional filters, okay? Yep. So roughly this pixel is now representing 4 different pixels, right? So if our image is 4 by 4, and then this single pixel is now representing 2 by 2 regions, right? And thus we want to represent that positions, the information that describes that positions in a much richer format. And so we use a more number of convolution filters, because we want to capture more number of diverse or various patterns. Okay, so you will see, or you will study more about this when we study specific architectures of this convolution neural nets, like VGG or Net or Google Net and so on. So that will be appearing in chapter 9. Any other questions? 네, 먼저.
뎁스 뒤로 가면은 뎁스를 늘렸는데
네.
필터 사이즈는 그러면 어떻게 지정해요?
필터 사이즈요? 이거 뭐 다 그냥 적당히 지정을 한 거고요. 네. 네. 그러니까 이게 꼭 정답은 아니겠지만, so how do we determine the exact number of filters that we have to use in a particular layer? So there is no right or no exact answer for this, and so there are many different choices, right? Yeah, but in general, some researchers found that that particular structure works well in the many different problems, and so so when you guys are trying to use convolutional neural nets, and then this architecture, I mean, that has that many number of filter channels, or the number of filters, yeah, you can just use that kind of a predefined architecture for your own task. Okay. 네.
스플링에서
네.
왜 2배가 되는지 128에서 250.
아, 네. 날카로운 지적이네요. 여기서 이제 맥스 풀링만 된 게 아니라 맥스 풀링 하고 나서 여기에 컨볼루션 필터를 적용해서 이제 128개의 컨볼루션 필터를 정의를 이미 한 거예요. 네. Okay, so yeah. So this is a good point. So from this activation map to this, we apply the max pooling, right? But in the case of max pooling layer, the channel is remaining the same, right? So max pooling is applied channel-wise, right? It only reduces the spatial resolution, but not the reducing or increasing the number of channels, because it's just applied at different channels. And so in this particular case, it is showing the result of the application of max pooling, and also another layer of conv and ReLU, where the convolution filter has 128 different filters. Any other questions? 네.
CS 231 강에서 잠깐 나온 것 같은데.
네.
다운 샘플링을 하려 할 때 맥스 풀링 말고 스트라이드를 아까 줄인다고 할 수 있다 하셨는데, 그럼 맥스 풀링의 장점은 더 못 쓰게 되는 거잖아요. 근데 왜 더 스트라이드로 하는 경우가 많다고 그래서 언급이 되는지.
옛날에는 스트라이드를 전혀 안 하고 했는데, 좀 요즘은 트렌드가 이제 또 맥스 풀링을 아예 배제를 하고 그 스트라이드만으로 해갖고 그냥 모든 레이어를 다 컨볼루션으로 구성을 하는 그런 식의 좀 트렌드가 좀 있는 것 같아요.
그럼 아까 맥스 풀링의 장점은 없어지는 거예요?
네, 맞아요. 네. 근데 이제 기본적으로 이제 렐루라고 하는 게 적용이 되면 이제 어느 정도 이렇게 양의 값으로 살아있는 것만을 우리가 살려주는 거잖아요. 그러면 어떻게 보면 굉장히 스트릭트하게 이제 우리가 딱 그 패턴이 나와야만 이제 0보다 커지고, 그 패턴이 조금이라도 불완전하게 나오면 다 이제 바이어스 값이나 이런 걸 작게 줘서 낮게 되면, 그러면 이제 그런 렐루에 의해서 약간은 이제 맥스 풀링처럼 이제 그 값만 이제 살아남게 되는 거죠. Yeah, so I think in the CS231 and lecture, yeah, so we discussed about the image resizing by half, right? So it is called the sometimes it is called downsampling. Okay, so that is resizing your image into a smaller size. Okay, smaller image, and this max pooling is actually doing the downsampling and also the convolutional layer with the stride size as maybe 2, and then it has the the effect of the downsampling by the factor of 2, right? So yeah, sometimes in some of the convolutional neural net models, we don't actually use max pooling at all, but also we just instead we just use a convolutional neural net. And if we want to resize or downsample the image, and then we apply the convolutional layer with the stride size as 2. Okay, so that is also another kind of a design choice. Okay. And also, in this case, we now downsampled our image out of 224 by 224 into 7 by 7, right? So image became really small, right? And then after then, it is representing the fully connected layer, because given these activation map, we just make them into a vertical kind of one-dimensional vector, and then just stack the a fully connected layer after then. Okay. And then the reason why we have a 1 by 1,000, let's just ignore this for now, but the reason why we have a 1,000 different number is because we are performing multi-class classification out of 1,000 different classes. Okay. And now, so if we just maintain these three-dimensional numbers as our kind of shape of the input and output activation maps, and then we can view this forming, we can view the step of forming the vector, okay, one-dimensional vector, so that we can provide it as a fully connected layer input. In that case, we can represent this as maybe 1 by 1 by 7 by 7 by 512. Okay, so it's like, so each horizontal vector is 512 dimensional, right? And different position, I mean, we have a 7 by 7 or 49 different positions, right? And then we just put those horizontal vector and then just concatenate it into one single vector. And then in that case, it can be viewed as maybe 1 by 1 by 1 by 1 by 7 by 7 by 512. Okay, so that's how we understand this fully connected layer. Yep. Okay. So in this particular case, if we view the shape of our activation map, and then we are losing the spatial resolution, right? Because the image size becomes smaller and smaller, and so the spatial information gets lost gradually. But at the same time, at each position, we have a richer representation. I mean, to represent each position, our vector was what? How many numbers did we use to represent a single position? It was 3, because each position was represented as a RGB as 3 different numbers. But at this position, at this activation map, each position is now represented as 512 different numbers, right? So now we can view it as having a rich information to represent each position, right? And then how about this? How about 1 by 1 by maybe 7 by 7 by 512? And then after applying the fully connected layer, and then suppose our output node is 4096. Okay, so suppose that is our number of an output node in the fully connected layer output. Okay, so in that case, we have a 7 by 7 by this number became reduced into 4096 numbers, right? But still, it can be viewed as 1 by 1 by 4096, right? In that case, we now represent an image as a single pixel, okay? Just a single pixel. Even though we started from 224 by 224 as all different pixel positions, but we now approximate or downsampled it into just 1 by 1, single regions. But that single region is now represented as a 44096 dimensional vector. Okay. So that way we can gradually lose the spatial resolution, but at the same time, at each different position, we actually represent each position into more, richer information by using a large number of dimensions. Okay. Okay, so so this kind of pattern is also kind of reversed. So this is a little bit advanced architecture, but yeah, you guys will study this in maybe after our midterm exam, but so let's look at just the patterns, okay? So up to this point, it is almost like the same as the convolutional neural net that we saw, right? So we gradually lose the spatial resolution, but the depth gets thicker, right? And then at some point, it is actually doing the reverse operation, okay? So now, this thicker kind of representation gets shallower, and then the spatial resolution now increases, okay? So it is like, it is called the encoder and the decoder structure. And when using that kind of architecture, our main application, our output is not a single number, but when our output is actually an image, okay? So if we want to obtain a particular image, and then this is the architecture that we use, okay? Okay, so this is the also encoder and decoder architecture, although it's just kind of a sectional image, but sectional kind of structure, but that is also used in the image colorization, where we give this black and white images, and then we want to obtain the colorized output, and then our input is an image and output is also an image. It's not like a single number that indicates particular class in the multi-class classification, right? So in this task, we do not just use only the encoder architecture, but also there are some decoder architecture that gradually increases the spatial resolutions, until we reach RGB representations. Okay. So we will study this in the later classes. Any questions so far? 네. 네? 어떻게 하는지요? 백프로브를 어떻게 하는지? 이거 백프로브이 이제 1000 디멘전에서 이제 로스가 발생이 되고요. 그 소프트맥스 로스가 여기서 이제 발생이 되고, 지금 요 레프레젠테이션은 이해 가나요, 다들? 요거는 그냥 이거를 1x1x 4096에서 1x1x 1000으로 간다? 그러면 이거를 이제 어떻게 볼 수 있냐면, 이걸 이렇게 버티컬하게 옆으로 뉘어서 이제 풀리 커넥티드 레이어가 구성된 거라고 보면 돼요. 여기서 이렇게 연결된 거예요. 오케이? 그러면 이제 백프랍은 여기서부터 시작을 해갖고 다 오겠죠. 다 오고, 여기서는 이제 요거를 리어레인지 한 게 이제 요거잖아요. 그죠? 요거를 이제 이렇게 한 줄 한 줄을 그냥 요 한 줄로 그냥 쭉 핀 게 그거잖아요. 그러면 요 한 줄로 폈을 때에 또 도착한 백프랍의 그 값들이 있겠죠. dy 같은 게 있겠죠. 그러면 그게 이렇게 리어레인지가 되면 그게 그냥 말 그대로 그 dy 값도 여기로 리어레인지가 되어서 이쪽으로 가서 붙겠죠. 그러면 이제 여기서와 여기서는 뭔가 이제 뭐 맥스 풀링은 맥스 풀링대로 백프랍이 일어나고, 이제 컨볼루셔널 레이어는 아까 이제 풀리 커넥티드 레이어 퍼스펙티브로 보면 이제 또 백프랍이 각 픽셀별로 dy가 할당이 되고, 그 전 인풋 액티베이션 맵에서의 또 그 dx가 계산이 또 되고, 그거를 만들어내는 데 쓰이는 컨볼루셔널 필터도 이제 학습이 되고, 이렇게 되는데, 이해가요? Okay, so this is the fully connected layer. You can understand this in a way that this horizontal vector is now rearranged or redrawn as the vertical vector. And then we can imagine the fully connected layer between these two vertical vector of 4096 as an input layer dimension and the output layer dimension as 1000. And then we would do the backpropagation just like what we do in the fully connected layer. Okay. And given this max pooling thing, so you guys understand this backpropagation on this max pooling, right? So if we have two different input node, and then it is like x1, so this is the max operation, right? And so if our forward pass or forward propagation had this value 5 and 3, and then we will apply this function, right? And then what about the back propagation on this? So current forward propagation has this 5, 3, and then in this case between these two functions we would use this function, right? And in this case, let's just ignore this part. So in that case, what is our partial gradient with respect to x1 and x2? Because we have two input nodes, right? And so, it's in the case of dx1, df over dx1 will be 1, and dx2 and df will be what? 0, because it doesn't involve x2 at all, right? So intuitively, suppose this is a max pooling output when doing the forward propagation, and then suppose our dy arriving at that position was maybe -2. Okay, so this gradient can be negative value, right? And then this value, when involving 4 different numbers, when doing the max operation, this -2 is just duplicated or just passed into this max value, right? And then what about all these other values? What are their corresponding gradient values? It will be 0, because as we can see, so the max operation between x1 and x2, I mean if x1 was max value, and then this is our max value, and that is our function at when having this forward propagation value. And so if we have an x1, x2, x3, and x4, and then max operation will pick up one particular value. And if it was an x1, and then the gradient with respect to x1 will be 1, and then all the other ones will have the partial gradient as 0, right? So intuitively, so in this case, we will have the backpropagation value or dy kind of value will arrive at this position, and when backpropagating through the max pooling, and then this dy is multiplied, dy is duplicated or passed into corresponding max value position, okay? So if it was a 7 by 7, and it would have is 14 by 14, right? And then each different value will be passed as the same value into one of the 4 different pixels, and all the other 3 pixels will have 0 gradient. Okay, so that's how we just backpropagation on this max pooling layer. Any other questions? Okay. And then these are one example of the activation map. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 different rows, and thus it means we have 10 different filters, right? And then so this is Not an important issue, but let me ask this question. So the activation after doing the ReLU is it's usually darker than the activation map right after the convolutional layer output. So why is it darker after passing the ReLU compared to the activation output from conv output? Okay, so in this conv layer output, suppose our activation map was 3 and -8 and 5 and -2 and so on, and then how we visualize them into a grayscale image is as follows. So here we have a minimum value, and we map it into 0 as an RGB pixel value and the max value as 255, right? But after doing the ReLU operation, so those will be gone, right? So now this 0 will be mapped into a completely black pixel, and 5 will still be 255. But what about this 3? Okay. So which one would be brighter when setting -8 as purely black, or when just a 0 as purely black? So the question is this pixel value in the middle, like 3. So which case will have the brighter color on this intermediate value like 3? Okay. So our signal has like this, and then we have a minimum and maximum, and this is a pure black and this is a pure white, right? And so we have some intermediate value, and so it is like brighter than average, right? But if we do the ReLU and then all these parts are gone, and so our activation will be something like this, right? And so this will be our pure black, right? And so this same position will now have a darker than the average, right? So that's why we have a darker kind of activation map, in this example. Okay, it's time to move to the next lecture. So have you guys understood this slide of this zigzag path? So so how about the parameters or weights in a fully connected, single fully connected layer or a single convolutional layer? Okay. So in this case, in case we use the in case we use the sigmoid, which is giving always the positive input, and also the ReLU is giving always the positive input or 0, right? So in that case, the gradient value will all be the same, when connected to a single output layer. So yeah, let me describe this situation in more detail. Okay, so x1, x2, x3. So I'm just representing this fully connected layer, although we have a bias, but let's just ignore it for now. And then, yeah, we have another output node in a single layer, but let's just fix output node as this a single one. And then suppose our dy or df over dy was maybe -3, right? And then suppose this x1, x2, x3 were set as 1, 2, and -3. And then what will be the gradient with respect to A, B, and C? So it is added together. So -3 is duplicated, and then this -3 times 1 will be the gradient with respect to A, and 2, which is -6, and +9 will be the gradient with respect to C, right? But here the main issue is that those input nodes of an x1, x2, x3 are not our independent input feature, but they are in general the output of the previous layer. Okay, so if our previous layer was the fully connected layer, and then passing through the sigmoid, and then x1, x2, and x3 are all positive values, right? And so given a fixed dy value, for whatever values that we multiply in order to obtain the gradient with respect to A, B, and C, they will all have the same signs, right? So basically, if those three nodes were the sigmoid output from the previous layer, and then it will be like 0.8, 0.3, and 0.5, and so on. So the main point is that all the input nodes will have positive values, right? And thus, if they are connected to the single output layer, and then single output layer has a particular gradient value, and then when doing the backpropagation, with respect to A, B, and C, and then because x1, x2, and x3 are all positive, and thus this sign will, the gradient of A, B, and C will all have the same sign, right? So at one iteration, yes, suppose, let's just remove this part, and then let's just consider the two parameters of A and B, and then so this is our A and this is our B. And suppose our optimal parameter value of an A and B were somewhere over here, which is maybe 3, -5. And suppose we started from here, maybe 0.1 and 0.3. And then this parameter at each iteration, it will be updated into like both negatively or positively, right? So in terms of a gradient, at this current position, the gradient will be always generated into this part or this part, right? But if our optimal value of an A and B are placed over here, and then the only way to reach or arrive at this position will be like this, which has the negative value, a large negative value with respect to B, and almost 0 negative value as our gradient for the A. Okay, so that way we have this zigzag pattern. Okay, so this is a kind of one limitation, of the situation where we have all the same signs of input nodes. Okay, input vectors has all the same signs, which is an activation from the previous layer. Okay, in that case, the updating of our parameters will be limited, okay, because they will be updated in by using all the same sign and a particular iteration, okay. So in order to overcome this situation, in general, it would be better if we have both signs that can occur at each different input node in our layers, okay. So that way, this sigmoid has the limitation, of having the same, always positive values. But this kind of thing is also adjusted through the batch normalization, right? Okay, so the time's up, and I feel I'm kind of slow, but I try to accelerate my explanation in the next class. Okay, and so please watch another video for the neural net or deep learning software, which is chapter or lecture 8.